I hope by now Dr. Ivy and I have convinced you that a rotating frame of reference is not an inertial frame. Now, you've all been told that the Earth is rotating about its axis, and that also it travels in a nearly circular orbit around the Sun. Why then do we find that in a frame of reference attached securely to the Earth that the law of inertia seems to hold? Why don't we observe fictitious forces? The size of the fictitious forces which we have to introduce in a non-inertial frame depends on the acceleration of the frame. The smaller the acceleration is, the smaller the fictitious forces that we introduce. Now, here is a frame of reference attached to the equator of the Earth. The acceleration of this frame is really very small. Because the Earth is spinning about its axis, it has an acceleration directly inward of 3/100ths of a meter per second squared. So on a 1 kilogram mass at the equator, there is a fictitious force acting directly upwards of 3/100ths of a newton. But this is masked by gravity, which is a force downward of 9.8 newtons. So the net downward force is smaller than that of gravity alone. So if I dropped a mass of 1 kilogram at the equator, the acceleration would be slightly smaller than that due to gravity alone, but not really very much. Now, the acceleration of the Earth in its orbit is even smaller still and produces even smaller effects in our frame of reference. Now, I said that the Earth was rotating about its axis. How do we know that this is so? Well, if you take a time exposure photograph of the stars, they seem to be moving in circles about the pole star. But all motion is relative. Is there any way of telling which is moving, the Earth or the stars? The fact that it is the Earth which is rotating can be demonstrated by means of a pendulum. If I set a pendulum swinging, it swings back and forth in a plane. Now, it turns out if this pendulum were at the North Pole of the Earth, the plane of swing would remain fixed relative to the stars, but would rotate relative to the Earth. Now, I'll have to show you what I mean. This pendulum is at the center of this turntable, which will represent the Earth. Now I'm going to start the table turning around in this direction. I'll put a black arrow on so that you'll remember. All right, start the rotation. The pendulum is at the North Pole of the Earth, and you are looking at its motion as you ordinarily do, standing on the Earth. The plane of swing rotates in the opposite direction from the rotation of the turntable and at exactly the same rate. Now look at it from the fixed camera, which will represent the frame of the stars. The turntable, the Earth, rotates, but the plane of the pendulum remains fixed. A pendulum used for this purpose is called a Foucault pendulum. You saw me start one at the beginning of this film. Let's look back again now. This Foucault pendulum drops sand as it swings. I think you can see the faint line where the sand trail began. The amplitude of swing is decreasing. The sand trail isn't as long now. But the important thing to see is that the plane of swing has been rotating during the half hour that we've been talking to you.
An inertial frame of reference is one in which the law of inertia is valid. All frames of reference moving at a constant velocity with respect to an inertial frame are also inertial frames. We use the Earth as an inertial frame of reference, but it is only approximately one. It has a small acceleration with respect to the stars, for example. The frame of reference of the stars is the best we can do when we look for a frame of reference which is, for all practical purposes, fixed.
An accelerated frame of reference is not an inertial frame. And when we are in an accelerated frame, we have to introduce forces. which we call fictitious forces, in order that the law of inertia and the other laws of physics don't change.